Okay, how are you going to present your work? So I'm going to show you how I'm going to write up the solutions that I just came up with. You don't need to solve the same problem in multiple ways, but you do need to clearly explain your solution approach. The answer is less important than the solution approach. So start by saying what's the general question you're answering, and then present whatever solution approach you have for the first variation you considered. So here I say, I first present a solution to this problem for 3 rooms of 3 people each. Then give an outline of the overall approach. So I will calculate the probability as the following. The probability we're seated together is number of seating arrangements where we're together divided by total number of seating arrangements. Then have a sentence or two kind of outlining the general approach you're taking for one of these pieces. So I compute the denominator by considering how many different groups we could assign to each room. And then I show what that computation looks like. So there's the computation. But it's going to be important that you explain to me all the bits. So why 9? Why 3? Why 6? Why are there 3 of these things multiplied together? So you could do that in sentences like this. So I've said there are 9 choose 3 groups for the first room because I'm choosing 3 people to be in the room from 9 people total. There are 6 choose 3 groups for the next room because I'm choosing 3 people from the 6 remaining. Finally, 3 choose 3 equals 1 is the only way to assign the remaining people to the last room. If it seems awkward to write it all out in sentences, you are totally free to do something like this. You can write down your expression on a piece of paper and annotate it by pulling out different terms and just saying briefly where does that term come from and kind of how does it make sense in the overall computation. So this is fine as well. Once you've explained all the pieces of the problem, show what they look like all together, and then simplify if you're able to. So that would be a full presentation of the one result. But you're not done yet because I want you to tell me as much as you can about the general question here. And we've just presented an interpretation of a specific version of it. So one nice thing you could do is work your same solution, but start to vary one of the 2 parameters. So you've got number of rooms, you've got room size. Let's keep it at 3 rooms, but let's increase the room size to 4 and see what happens. So here's my solution. I applied the exact same approach, except this time I get a probability of 3/11ths. And because it was hard for me to compare 1/4 and 3/11ths, I also wrote a decimal approximation because that seemed to be more revealing. Okay, so my intuition says that as the rooms get larger, I should have a larger chance of sitting with my friend, and it seems like that's what's happening so far, so that's good. My sense check has worked. Let's go another one. Okay, so now with a room size of 5, I'm getting a 29% chance of sitting with my friend. With a room size of 6, I'm getting a 29.4% chance of sitting with my friend. So something interesting seems to be happening here. I'm curious about the fact that while the probability is going up, it seems to be going up by a smaller and smaller amount. And that's making me wonder, it seems like it's getting closer to 30 to me. Is it possible to break 30? Is it possible to get, could the room sizes get so big that I have a 50% chance of sitting with my friend? Maybe you have an intuition about that, maybe you don't. Let's try and generalize. Instead of presenting a sequence of results, let's make the room size be a variable, n. Okay, so here's my expression, and I just wrote it here, but this takes some thinking about. You got to think all right, 9 choose 3, 6 choose 3, 3 choose 3. If I have a room size of n and 3 rooms, that means there are 3n total people, and I'm choosing n of them for the first room. And then there's only 2n people left over because I've subtracted n people from my original 3n people. So you gotta be able to kind of generalize and think about it. But once you've come up with a general expression, this could be an equation that you could graph. You could look at n, and then here would be the probability, and you get to see what does that look like. But not until you can simplify it a little bit. So you should then go through some work and see if you can simplify it. Here's what I'm going to do. So first of all, those terms cancel. Then remember that a choose b has an equation, and it is a factorial divided by a minus b factorial times b factorial. So if I apply that kind of pattern to those two combinations, I'll get this. Okay, so that looks kind of messy. But let's, I think that this can probably be simplified a lot. Like already, do I notice anything already? Well, here, let's simplify the part in here. So 3n minus 2 minus quantity n minus 2. So if I've got 3n minus n, that's now 2n. And then I've got a minus 2, and then I'm going to subtract another minus 2. Or sorry, so I've got minus 2. Let's distribute the negative sign. That'll make it easier for you to see. So if I distribute the negative sign, I've got minus n plus 2. So now the minus 2 and plus 2 add to 0. And so now I've got 3n minus n is 2n. So that's all simplified very nicely. And now down here I see 3n minus n, so that's also 2n. Aha, this is working out well. And so then 2n cancels with 2n. Maybe let's multiply by the reciprocal. So here I'll do, this will be 2n factorial, and this will be 3n factorial. All right, so that's now the same. So now I'm noticing 2n factorial cancels with 2n factorial. So let's rewrite this now all on the next line. All right, there we go. So I wrote my n minus 2 factorial here, and I wrote my 3n factorial there. This can still simplify even further, though, because if you think about what's n factorial, that's n times n minus 1 times n minus 2 all the way down to 2 and 1. And then what's n minus 2 factorial? It's n minus 2 times n minus 1 all the way down to 2 and 1. So what I'm seeing is the n minus 2 factorial is going to cancel the entire ending part of the n factorial, leaving me with just n times n minus 1. So let's do that cancellation. Here I'm going to cancel this with that, and it leaves me left over with n times n minus 1. And then the same thing is happening over here. In the denominator, 3n factorial is like me saying 3n times 3n minus 1 times 3n minus 2 all the way down to 2 times 1. Because remember, 3n is my biggest number, and I'm just subtracting one number for each new thing I'm multiplying by. 3n minus 2 factorial in the numerator here is 3n minus 2 times 3n minus 1, and so on, all the way down to 2 times 1. So same thing's going to happen. These are all going to cancel, leaving me with just 3n times 3n minus 1. So let's do that cancellation now, and let's write the whole thing over here. So I've got 3 times n minus 1 in the numerator, because I had that. Then this is going to cancel with that, leaving in the denominator 3n times 3n minus 1. So this is a much easier to deal with equation because we don't have any combinations, we don't have any factorials. And this is giving me the probability of me and my friend sitting together with 3 rooms of size n. And now that I've got an equation, let's graph it. Okay, here's what it looks like. Let's interpret this. So here's a room size of 1, and clearly there's a 0% chance that me and my friend will get assigned to the same room if every room has 1 person in it. Here's where the rooms have 2 people in it. So if the rooms have 2 people in it, that gives me a 20% chance of being with my friend if there are 3 rooms of 2 people each. And then it keeps going up from there. So let me restrict the domain here. Let me see if I can remember how to do this. Yeah, okay, there we go. So restricting the domain, we have something that looks like this. Let's try and evaluate P for a large. So like, let's say room size. So if I have room sizes of 100,000, so it looks like I'm approaching a probability, I'm approaching a probability of 1/3, which actually kind of makes sense if you think about it. But this would be now a great general result to add to your paper. When you present your results in your paper, You don't need to include all of the algebra in line because I'm mostly interested in seeing your approach and your results, but the details of the algebra are less important to me. So here I say let n be the number of people per room. We will keep the number of rooms at 3. And then I give the generalized equation that I generalized from here. And then I just assert that it simplifies to be that, but I didn't show the algebraic work there. And then I present my graph, and then I interpret the graph. I say it appears as if limit as the room size approaches infinity of my probability equals 1/3. In other words, as room size approaches infinity, the probability of us sitting together approaches 1/3. So this would be sort of like the best possible outcome for your exploration of a problem is, 1 second. So we started by interpreting the problem for a very specific scenario. We did a lot of hard thinking to come up with a solution for that scenario, which we then presented. Then we take our solution and we try and generalize it. And if you can't get an equation, that's okay. You could still present a table of values where you kind of explore what happens as you vary one of the aspects of the situation. But ideally, you'd be able to come up with an equation. If you're not able to simplify the equation, that's okay, but ideally you would be able to simplify the equation. And if you can, then you can start exploring it using other representations like graphs, and you can interpret the results of the graphs. Good luck, everybody!